Welcome back to the deep dive. Today we are plunging into, well, let's call it the hidden world of industrial steam generation. We're talking power plants, huge manufacturing facilities,
Wow.
places where some of the biggest problems aren't, loud mechanical failures,
Right.
but things you can't even see. Dissolved gases, microscopic flow patterns,
Yeah.
stuff that's quietly eating away at the system.
It really is a silent thread in engineering.
Ugh.
And today we're focusing this deep dive completely on boiler water and steam condensate corrosion.
Okay.
Our source material is very focused. It's about mechanical integrity, identifying the three main drivers of damage:
Yeah.
dissolved oxygen, O2, carbon dioxide, CO2,
Right.
and the one that, well, often catches people by surprise, flow accelerated corrosion, FAC.
FAC. Okay, so our mission today is pretty straightforward then.
I think so.
Give you, the listener, the shortcut to understanding this pretty complex chemistry. We're going to break down the critical factors, pH, temperature, gas levels, things that really matter, and lay out the protective measures needed to, keep these huge systems running safely. Basically, if you need the quick version to sound smart on boiler integrity, this is it.
And here's maybe the first aha moment for context.
Yeah.
While the chemistry gets complicated, the materials getting hit hardest are, well, they're pretty basic.
Oh,
We're
wow.
talking carbon steel and low alloy
Your
steel.
standard pipes and tubes.
Your standard pipes, heaters, boiler tubes, yeah. The absolute workhorses. And they need constant, like minute-by-minute protection.
Okay, let's unpack that. Starting with the classic chemical attack. Dissolved gases. This seems like where the trouble often starts.
It often does. And if you look at the damage, the way it looks tells you which gas did it.
Ah, interesting. So the appearance is a clue.
Definitely. The two main gases we mentioned, oxygen and carbon dioxide, they leave different fingerprints, let's say.
Okay, start with oxygen. What does that look like?
Oxygen causes pitting. So not general thinning, but small, deep holes.
Yeah.
It's very localized, very aggressive. And the sources highlight it's particularly bad where water temperature jumps up quickly. Think closed heaters, economizers.
Okay, wait. Define economizer quickly for us.
Sure. It's just a heat exchanger. It uses waste heat, usually flue gas, to preheat the boiler feed water before it hits the main boiler drum.
So it's where the water starts getting seriously hot.
Exactly. And that temperature spike makes any dissolved oxygen in the water way more reactive. And the scary part, as you said, is even tiny amounts of oxygen getting past the treatment system. They can start this aggressive pitting.
Okay, so that's oxygen, nasty little pits. Now, how does that compare to the second chemical threat, carbon dioxide?
The CO2 is, well, it's a different beast. It dissolves in water, forms carbonic acid.
Ah, acid. Right.
And this attack, carbonic acid corrosion, it usually looks like smooth erosion, kind of general thinning.
Smoother than pitting.
Yeah, but it can also cause grooving, especially in high flow areas, little channels carved in the pipe wall.
Okay.
And this is a really common problem, especially in the condensate return system.
Why specifically there, condensate return?
Right, think about it. CO2 gets stripped out of the feed water earlier on, hopefully. It travels with the steam as a gas, no problem.
Okay.
But then way downstream, that steam cools and condenses back into water in the return lines.
Ah.
And
yeah.
boom, the CO2 dissolves back into that fresh condensate, makes carbonic acid right there, often where the metal isn't as well protected.
Yeah.
And the temperature is lower.
Got it. So oxygen, fast, localized pitting, CO2, slower, maybe smoother thinning or grooving, especially in condensate lines. Where else do these attacks happen? Is it just pipes?
No, unfortunately, it's pretty systemic. You see it in the dereator itself.
The thing designed to remove the gases.
Ironically, yes.
Mm-hmm.
And then downstream, feed water lines, heaters, economizers,
Right.
the boiler tubes themselves, and all that condensate piping we just talked about.
Mm-hmm.
And it can be very localized sometimes, like right at the water line, the interface between water and vapor in something like a vertical reboiler. That's where gases can concentrate.
And that leads to something I saw mentioned, threaded connections. Why are they called out as being particularly vulnerable?
That's a great point. It's about geometry.
Yeah.
Those threads, or any fitting really, like an elbow or a flange, they create turbulence.
Right. Interrupts the smooth flow.
Exactly.
Yeah.
And that turbulence can help concentrate the corrosive stuff, let it hang around and attack unevenly. But that idea, flow and geometry, that takes us straight into the second big problem, flow accelerated corrosion, FAC.
FAC. Okay, this one's different, you said. Not just chemical.
Right. It's fundamentally flow driven.
Yeah.
To get FAC, you need to understand how these systems protect themselves normally.
Okay.
It all relies on keeping a stable layer of a specific iron oxide, magnetite, FF304 on the inside surfaces.
Magnetite, like a protective rust layer.
Sort of, but it's a good rust.
Yeah.
Think of it like a hard ceramic coating almost. It forms naturally under the right conditions and shields the steel.
Gotcha. The system's armor.
Perfect analogy. Now, FAC, that's when this protective magnetite layer gets dissolved away too quickly by the flowing water, where it gets physically scoured off or just can't even form properly because the flow is too aggressive.
So the armor gets stripped away, exposing the bare metal underneath.
Precisely. And then the corrosion happens very fast.
And what conditions make this FAC process really take off? Are there specific temperatures or water chemistry factors?
Yes, the sources are very clear on this. There's a peak danger zone for temperature. The single most critical temperature for FAC is 300 degrees Fahrenheit. That's 150 Celsius.
300 F. Wow, very specific.
If your water's flowing fast in that temperature zone, you're at maximum risk for FAC.
Okay, what else?
pH is huge. The corrosion rate drops sharply as the pH goes up.
So alkaline conditions are good. High pH protects against FAC.
Absolutely critical. Keeping the feedwater pH high is a primary defense against FAC.
So just to summarize FAC, it's not just rust, it's the protective layer getting stripped off, mainly around 300 degrees F, and it gets worse at lower pH.
You got it. And visually, the damage looks different again. FAC usually causes general wall thinning, not pits.
Okay.
But the key is where it happens. It's very specific, just downstream of flow disturbances.
Ah, so right after an elbow or a valve or where a pipe narrows.
Exactly. Any fitting that makes the water suddenly change direction or speed up. The turbulence hits the pipe wall right after that point. And the surface looks kind of scoured clean, no magnetite scale left. Often you can even see flow patterns etched into the metal.
And the danger is?
Rapid, widespread thinning in that area. It's not a tiny pit. It's a larger zone losing thickness fast. That can lead to a certain catastrophic rupture of the pipe.
That sounds terrifying. I did notice a material science point, though. Adding things like chromium, copper, molybdenum.
Yeah.
Those help.
Yes, definitely. Upgrading to low alloy steels with CrQ, Obiscabo significantly boosts resistance to FAC. It makes that magnetite layer tougher or helps it reform faster.
So better materials are an option, but usually expensive, I assume.
Very. So before you rip out piping, you focus on the chemistry.
Yeah. Which brings us neatly to mitigation. How do we fight back against all this? Let's start with standard prevention. Oxygen removal.
Step 1 is mechanical deceration. Basically, you boil the gases out of the water under pressure and vacuum.
But you said that's never perfect?
Right, so you follow up with chemical scavengers, typically catalyzed sodium sulfite, or for higher pressure systems, hydrazine.
Hydrazine sounds potent.
It is. These chemicals react with the remaining oxygen to neutralize it. And crucially, you need to maintain a small residual amount of scavenger in the water going to the boiler.
A little bit extra, just in case.
Exactly. That residual is your safety net. It mops up any oxygen that might leak in later, protecting those heaters and economizers from pitting.
Makes sense. Okay, what about dealing with the CO2 corrosion back in the condensate system?
Well, keeping the pH right helps, but if that's not enough, you often need specific inhibitor treatments.
Amines.
Yeah, they're chemicals that travel with the steam, condense with it, and then neutralize the carbonic acid or form a protective film on the metal surfaces in the condensate lines.
Clever.
Also, basic maintenance is vital. Making sure vents that release non-condensable gases are working, and ensuring steam traps are doing their job.
Steam traps, they drain away the condensed water, right?
Exactly. If they fail, water backs up, CO2 gets concentrated, and the acid attack gets much worse.
Okay, now, let's get to what sounds like the most counterintuitive part, the oxygen paradox.
Ah, yes. This is a big one.
We've just established oxygen is terrible, causes pitting, yet the sources say zero oxygen is not actually the goal anymore.
Correct. This is a major shift from, let's say, traditional boiler water thinking. For decades, the aim was get oxygen down to zero.
But not now. Why?
Because of FAC. It turns out that to form and maintain that crucial protective magnetite layer, that armor plating, you actually need a tiny, tiny amount of oxygen present.
Wait, seriously, we spend all this effort removing it using chemicals like hydrazine, and now we need some back.
Sounds crazy, right? But yes, the current understanding, based on the sources, is you need at least 3 parts per billion, up to maybe 7 ppb of oxygen.
3 to 7 parts per billion. That is an incredibly small window.
It is minuscule. But if the oxygen drops below that 3 ppb threshold, that protective magnetite layer becomes unstable or can't repair itself properly, and FAC corrosion actually gets worse.
Wow. So the very thing that causes pitting, oxygen, is needed in trace amounts to prevent FAC by stabilizing the magnetite.
You nailed it. The poison, in tiny doses, helps maintain the antidote, which is the magnetite layer.
That explains why the chemical monitoring has to be so precise. Living in that 3 to 7 ppb range requires constant vigilance.
Absolutely. And it drives specific actions for FAC control. Besides upgrading materials to CRMO steel, which works but is costly,
Right.
engineers now use what's called oxygenated treatment. They might actually control tiny amounts of oxygen, or, more commonly, they reduce the amount of oxygen scavenger they add.
To deliberately let that tiny residual oxygen level stay within the 3 to 7 ppb target range.
Exactly. It's all about maintaining that sweet spot to keep the magnetite healthy and suppress FAC.
And speaking of sweet spots, what's the target pH range again for the feedwater, specifically to minimize FAC?
Very tight band. Recommended boiler feedwater, or BFW, pH is 9.2 to 9.6.
9.2 to 9.6. Not much room for error there either.
Nope. Drop below 9.2 and FAC rates can really climb.
Okay, this brings us to keeping watch, monitoring. All this delicate balancing relies on knowing exactly what's in the water, right?
Constantly, you need rigorous sampling and lab analysis.
What are the key things being measured?
Well, obviously pH conductivity tells you about total dissolved solids, alkalinity, hardness, and a chlorine or a biocide residuals.
And the gases, of course.
And definitely the dissolved gases, O2 and CO2. Plus, you track indicators of ongoing corrosion, like levels of iron and copper in the water.
Spikes in iron or copper mean your system components are dissolving.
Exactly. It tells you the protective layers are breaking down somewhere.
That's the chemistry check. What about physically inspecting the equipment? How do you find that FAC wall thinning before a pipe bursts?
Good question. For finding air leaks into the system, like into the condenser hot well, you might use vacuum testing.
Okay.
But for checking the pipe wall thickness itself, we rely on standard non-destructive testing, NDT, mainly UT, ultrasonic testing, and RT radiographic testing.
UT is sound waves, RT is like X-rays.
Basically, yes. UT bounces sound waves off the back wall of the pipe to measure thickness. RT gives you an image, like an X-ray, to look for thinning or flaws.
Vital tools. But here's the kicker. Can you do this while the boiler is running, making steam and money?
There's the rub. Can we do UT and RT online?
Yeah.
For the most critical parts, like inside the boiler tubes or on high-pressure piping? No. There are really no practical online inspection methods for that level of detail.
So you have to shut down.
You have to wait for a scheduled outage. All that crucial UT and RT work happens when the system is offline.
Which just highlights why getting the chemistry right, maintaining that 3,7 ppb oxygen, keeping the pH at 9.2 to 9.6, why it's so incredibly important.
It's paramount. Because if you mess up the chemistry, you might not know the damage is happening until the next shutdown. Or worse, until something fails. The costs of failure are astronomical.
So wrapping this up, what's the big picture takeaway for someone managing or working with these systems?
I'd say managing boiler corrosion isn't a set it and forget its task. It's a constant balancing act.
Right.
You're juggling precise chemical treatment, smart physical design to minimize those flow disturbances we talked about, and choosing the right materials.
And constantly checking.
Sampling, analyzing, adjusting, and using those precious shutdown windows wisely for inspection.
Okay, final thought then. Let's go back to that oxygen paradox one last time. It's fascinating. Oxygen, the enemy, but also needed in a tiny specific amount for protection. Does learning about this critical minimum level for something generally seen as bad change how you, the listener, think about other complex systems, maybe in environmental science or other industrial processes?
It's a great point. The optimal state often isn't zero. It's about finding and maintaining a very specific, sometimes narrow, beneficial range. Complete elimination isn't always the best answer.
A delicate balance indeed. It's something to think about.
Absolutely.
Great stuff. Thanks for breaking that down. We'll talk to you next time on The Deep Dive.